Um, Today we have Luka from Mathematical Institute of Serbian Academy of Sciences and Arts, talking about what he does in his field of research. Luka, take the lead.
Thank you, Dusan. And thank you everyone for coming here today. As Dusan said, I'm going to talk about optimization. And I thought about the audience for this lecture and what would be interesting for you. So I actually decided to speak how C++ can be used for these optimization problems. And first of all, we will discuss what are optimization problems, why do we need them, why do we use C++, why not something else. And finally, I'm gonna talk about something that I did. Basically, it was published at a journal, and later it became a part of my dissertation. And this is going to be basically a case study for this type of problems. So why would we use it? Well, performance is basically the main argument for it. You need every bit of computational power that you can get. If you're wasting your computational power on something else like interpreter or virtual machine manager or something like that, you don't want to do that. You want to just use the best possible performances for your basic solver, for your optimizer. So why C++ and not C? Well, C is totally legit answer, and most of the solvers that are commercial are actually written in C, but they leave you the possibility of using that API in C++. And I would definitely argue that it's better to use it in C++ because you don't have to worry about many things. We will see. I mean, you do have to worry about this concept like freeing memory and all of that. It's just, it can be done in much easier way than you would do it in C. In C, you get a big piece of code, and very often it's harder to read than objective-oriented language. So when it comes to maturity, there are many libraries, profilers, but I would also argue that maybe they are not enough. I will actually give you one example where this can, if someone wants to make a C++ project to put on GitHub or something, I will give you an idea. But it's simply, there's simply not a good way, not a reliable way to, not a good library for calling those solvers. You would actually have to know this C API, and this could benefit from a C++ library that wraps those API calls. So I'm gonna talk a little bit about this problem that we are going to explore and give you a mixed integer linear problem formulation. And I'm not going to go into details for a simple reason that it's just a bunch of mathematical notation, and I will tell you what is important to remember from that and what's not important. But okay. So, what is a vehicle routing problem in general? You can see that we have some central depot, and we want to serve some number of customers. All of these customers, these blue dots, represent customers, and we have a limited amount of vehicles. We want to decide which vehicle actually going to visit which customer and in which order. You can see that if we have only one truck, only one vehicle, it is actually a traveling salesman problem. So when number of vehicles is one, it's traveling salesman's problem. This is why it's a generalization of that problem. So in this image, you can see that from those initial customers, we created 4 routes that are going to be traversed by 4 trucks. Of course, there are many different versions of this problem. And these specific criteria are called attributes of the problem. So, for example, the very common one is the one where you actually have to take into account the capacity of the truck, of the vehicle. Of course, if you're serving your customers and you don't have enough space in your truck to serve them, it's not going to work. So, that is something that is almost always considered. But there are actually many others. For example, customers might want to be served in the exact time window. So you have to serve them when they are at home. If, they told you, I'm there from on Friday from 2 p.m. to 3 p.m. You have to serve them in that window. So that is another constraint. There are actually many of them. You can actually form, I don't know, basically infinite numbers of these problems. Uh, why don't we? Well, we often do. That's how we publish papers. But in general, you would actually want to find some useful versions of the problem, something that can be actually used in industry. Because if you just put a bunch of attributes together, which would never go together, that's not really useful, right? So, what is attribute that was one of the attributes that was actually looked at here? It was about routing of electric vehicles, and since they have much more limited range, now it's actually much better when it comes to range. But in general, you want to take their range into account, and you want to take into account that when they deplete their battery, you cannot just go to some gas station and fill up the tank. You need to spend some time, and now that time can affect, for example, those time windows that we were talking about. So you have to take that into account. And I think I have. Oh, I have. Okay, if you're starting from depot, we serve customer C1, for example, and we are left with 60% of the battery. Then we serve the customer C2, and we are left with 35% of the battery. And then we have to go to some alternative fuel station where it would actually spend some time until it reaches again 100% of the battery. Would we always be there until we are at 100%? Well, no, that is also partial recharge attribute. We are not going to discuss it here, but if you're interested, I have papers about that as well. But in general, you want to recharge your battery and then continue serving your customers. At no point can it happen that your your vehicle is somewhere on the road without with a depleted battery, because that's not a good position to be at. Because with your internal combustion vehicles, you can just go to the gas station, bring some bottles with you. You know, we all been to the 90s. We all been there. So you cannot do that with electric vehicles. What are you going to do? I mean, take out that big battery that is beneath your car, put it on your back, and then go somewhere. It's not gonna work. You would need to go. You would need to call someone to take your car somewhere else. It's not a good position to be in. So that is something that can definitely not happen. That shouldn't happen. And we also considered several other attributes. In this case, it was soft time windows, which means that we would actually try to serve our customers when they prefer. But if we cannot, if we actually arrive a few minutes earlier or a few minutes late, um, that would be fine with some penalty. We would penalize those solutions, but we would say, okay, it's fine, it can happen. Also, time dependent speeds are something that is very useful when you have this uh, in the last mile delivery, as they would call it, which means when you deliver your goods in the urban area, because you cannot say that from point A to point B the distance is going to be the same from point B to point A. Uh, First, we have many one-way streets. Then somewhere you can actually encounter some congestions. So it's very realistic to look at time-dependent speeds. Um, and how do they? What do they depend on? Well, they depend on the time of the day. That is how this is modeled. For example, I think we said that from 6 a.m. to, I don't know, 7 or 8 a.m., the vehicles are going fast. After that, they are going to be slowing down a little bit because it's a morning rush. Then later, when people are going back from work, the vehicles are probably not going to go the same speed. So we tried to model this, and we found some papers that that actually showcased how this time of the day actually um, affects the speed of the vehicle in vehicles in the city. And it is actually inspired by a real life case. The first data that we got was from Univer Export and their delivery system. So we started from there. Um, we made some assumptions that all vehicles are the same and they fully recharge at each station. Energy consumption is linear, which this is a very big assumption that is not true in the real world. Also, what is also not true is that charging function is not linear. It's actually, um, well, it's not linear. But we made this assumption, and I will tell you later why this is important for these exact solvers and not important at all for metaheuristics. So, vehicle routing problem is NP-hard problem, and all of the variations of it, like the one that we just discussed, is also NP-hard by its nature. And here is something that that I really like. I show this picture so many times. So when you have this type of problems, you have many ways to deal with those problems. But the biggest distinction is whether they are exact solvers or approximate algorithms. So what are the exact solvers? They actually find the best possible solution, and they give you guarantee that the solution is the best possible one, but they take a lot of resources. On the other hand, approximate algorithms, they don't actually give you the optimal solution. They can find it, maybe, but they cannot guarantee that it is optimal. Uh, Actually, this class of approximation algorithms, they can actually give you guarantee that solution is not worse than some predefined threshold. Uh, they are not the ones that I researched. But heuristics are generally much easier. often deterministic, but not necessarily. And metaheuristics are much more general purpose algorithms for finding solutions for these optimization problems. So heuristics are usually problem specific. You have heuristics for a specific problem. But meta-heuristics can work with pretty much any problem, but they can use heuristics as their routines, basically. When it comes to exact solvers, we'll talk about that a little bit more, but a little bit later about that. Math heuristics are very interesting. They are a combination of meta-heuristics and exact algorithms. So we are trying to leverage the best in both worlds. Sometimes that works, sometimes we get the worst of both worlds. So be careful with that one. And this is something that I decided maybe to skip, because here I'm trying to actually give it the mathematical formulation for this problem. But what is actually important to remember is that for this exact solvers, we need to give it our problem in the form of some mathematical expression. In the sense, we give it, we define the objective function. We first decide on decision variables, and the decision variables are the variables that for which we need to find the values. They represent our solution. So these decision variables, they are basically our solution. And when we find the best values for them, that is our solution. That is basically what exact solver needs to do. And this is objective function. So we used some decision variables, and our solver needs to find this x of ij. So it is there are some variables, and it will actually find the best ones. So what is the important thing to remember about this? These variables are basically, they can be binary, they can be integer, or they can be real values, like from the set of real numbers. And this is a little bit complicated. And what do you think? If you actually made all variables to be from the set of real values, would that make this problem easier or harder? Can anyone guess? Yes. It would make it easier. So why is that so? I mean, when you first look at it, it seems like if they are integer, it is probably going to be easier, because the less values each variable can take, right? But we actually have very good mathematical algorithms for solving this type of problems when all variables are real. And I'm sure that all of you heard at least about one, which is always used. It's simplex method. You all heard about simplex method. It is something that is usually done first year computer science. So we can actually find these solutions very easily. But the moment we have these discrete variables, then not so much. Then it becomes much harder to model this. And yes, I'm going to skip this, but remember that we actually have decision variables which we need to find, and we have constraints. And constraints are just telling you which values can these variables take. And these constraints in this case needs to be linear. If you have nonlinear, that's going to create problem because then these solvers cannot solve it. There are nonlinear solvers, but it's actually even more complicated. And that is why when I said that we have this nonlinear charging functions and all of that, this would be very problematic for exact solvers, but not so problematic for metaheuristics. Okay, we have, at this point, we have some mathematical model, and we gave it to the solver. For example, you have a Cplex, which is a commercial solver, but GLPK is also another one, which is a GNU linear programming kit, which is the one that I'm going to talk about today. So, what is the point of this? It had provably optimal solution. It can actually prove that the solution it found is actually optimal, but it's actually slow. It needs a lot of resources, so um, the usability in practice is actually very limited. It's not scalable at all because for for this particular problem, I was able to solve um, this problem for small instances, like 15 customers. After that, it's very hard. You don't get any good solutions. So there are actually many of these solvers, and as you can see, most of them are written in C or C++. Exactly because of what we talked a little bit earlier. Um, we need performance for this type of problems, and all of them expose some API to the user so that we can actually give that mathematical formulation to these solvers. And GLPK actually gives us the C library, which is not very easy to work with. Here's how it basically works. I mean, you can create these problems, and then you add columns and rows. Columns are actually representing your variables, and rows are actually representing your constraints. Now the problem with this is that when you're writing something a little bit bigger, some bigger model, it can easily become unreadable. So this could actually benefit from some C++ wrappers, which is what I actually said earlier. There are not many good C++ wrappers for this because it's very niche use case, and not many people are doing this, but this could actually be very useful because Python did something similar. Python did, you have Pyomo, which is a package for Python, which allows you to connect to these solvers, and it is actually done very well. Why is it not a problem that it is in Python? Because we're just defining a model, and then it is actually translated to C, and the solver is called in C. But as you can see, this is not really. This can easily become unreadable, especially when you have a bunch of constraints. For example, for this model, I think there is 26 sets of constraints. So it's not so easy to write. So we could actually use from making we actually use some wrappers around this. For example, like this, we can actually initialize it. You all heard about this. Resource acquisition is initialization. This aspect, as an aspect, it's Actually, we can use this to initialize our model and to destroy it when we create the object of this class. So it's going to be much better. Now, I don't have with me, I have on my USB flash, but let's not go into that. The implementation in C, and what you would see at the end of that file is like 20 or 30 free commands, free functions. So it can become very complicated. What did you free? Which memory did you free? Which one you didn't? After sometime it can actually become more problematic. So this would actually solve this problem. But in general, the main idea of this is to see that you can actually use C and C++ to optimize these type of problems. Now, all of this is just some implementation, and I'm sure that all of you can just read the documentation. But the main point of today's talk is to see that there is actually an option for things like that. You just need to define that mathematical model and give it to some C or C++ solver, and you're going to get the result eventually. But if you don't like that eventually, then we are going to talk about metaheuristics. And we already said that this can work for small instances, but for the larger ones, this is not going to work. But what are metaheuristics? Well, they can actually find you a good enough solution in a very short amount of time. And the problem is it's not it doesn't guarantee you that it's gonna be optimal solution, but it's gonna be a good enough. I mean, if you go from here to Karaburm and you found a solution that is maybe 200 meters longer than the optimal one, who cares? I mean, you actually got the solution in like 10 seconds instead of waiting 10 days. Those 200 meters, it is acceptable. So you use it when you actually can afford this inaccuracy. If you cannot, then what can I say? You have to use those exact ones. And there are actually a bunch of these metaheuristics. When I was doing my PhD, I actually managed to count more than 500 of them, and that is without variations. Right now, there are even more than that. I mean, surely there are more than that. But basically, how I would classify them, some of them are single solution. Those are usually trajectory based, and some of them are population based, where you have different instances of solutions, and then you try um, to optimize all of them at the same time, trying to cover the more space, as much space as you can, because you are trying different parts of the search space. While trajectory based is much more um, how would I say? It search usually smaller amount of space, but it can traverse it better. So when would I use this population base? Generally, when I have some insanely big search space, and population based metaheuristics would help me to find good enough subspace of that search space to find some promising areas of that search space. And then you can actually switch to a trajectory based, like variable neighborhood search, which would actually help you find the best possible solution in that area. But it's not gonna work if it has to jump to some completely different part of the search space. So you can combine them, and very often they are combined. This is some basic diagram how I structured uh, this code, because I cannot actually show you now the entire code. Maybe after the lecture, if you want to know. But in general, we have some class for solution and class for roots inside the solution. And here I defined all the methods for manipulating that solution in terms changing it, copying it, and everything else. Calculating the objective function, or to say differently, the fitness of the solution. Uh, and utilities, I have this class where I define some neighborhoods for that I would need for these metaheuristics. Of course, we have data which represent the specific instance that we are trying to solve. And I did several metaheuristics. In general, I don't know why I don't have the best one here, but okay. Um, Today I will only talk about variable neighborhood search, and even that briefly, so I cannot really go into all of those. But spoiler alert, it was actually mimetic algorithm which gave us the best solution, statistically the best solution for this problem, which is basically a genetic solution with some single solution strategy, um, where you actually refine some solution in that population. But okay, I don't have time for that right now. But let's talk a little bit about variable neighborhood search, which is a single solution meta heuristic which was developed by Mladenovic and Hansen in 1997. And it has three steps basically: shaking, which changes the solution randomly in some neighborhood, which means take some neighborhood that is k steps away from your current solution and choose a random solution from that neighborhood. In shaking step, we don't want to find a better solution. We just want to go far enough so that we don't get stuck in some local optima. In the local search, we try to refine that solution. We go through different neighborhoods. We use local search by changing a solution a little bit, evaluating it, and after we evaluate it, we decide whether it's better than the current solution, whether it's worse. If it's better, then we go to neighborhood change, uh, which actually changes the neighborhood we are currently in. You can see this. If we start from x min 0, the first x prime, that is something that we decided randomly in shaking step. X secundum is something that we found in local search. As we didn't find the better solution, we moved to the next neighborhood, the N2. So you can see that in each neighborhood, we are going further and further from our current solution. That's the idea. At some point, we do find some better solution, and we moved to it. So basically, all routes are implemented as vectors, actually as double-ended queues, because it gives us better performance in terms of um, accessing elements and deleting them, adding them. For some reason, this implementation is like O1. It can actually access them in constant time, even though it's a tech queue. So that's we have arrivals, departures that is connected to those time windows. But we do have random access in constant time. That is why it's used, DQ is used. And we define some neighborhoods, which I'm not going to talk about today because it's not that important. Each in the neighborhood, it's basically written as a C++ method. Here we actually calculate the traveling time from some point E to point I to point J. Um, but yeah, I don't know what I would actually. I wouldn't like to go through the code itself, but this is a local search method, which is called variable neighborhood descent, which is actually quite easy and quite effective. Because we first try some neighborhood. If we find some better solution, that's great, we accept it and we go back to the first neighborhood. If we don't find anything that is better, we go to the next neighborhood. The moment we find a better solution, we go to the first neighborhood and try again, but first we accept the better solution as the new current one. It is actually quite effective, but um, we have to limit the execution time of this method because it can eat up a lot of time, a lot of processing power. Because as you can see, it can go back and back to this first neighborhood. Every time it finds a better solution, it can go back to this first neighborhood. And yes, it's still optimizing the solution. It is still finding a better solution, but maybe you would be better off to just try to see maybe in other parts of the search space, maybe there is something better instead of optimizing this particular area. Not all of these neighborhoods actually were equally good in were performing equally well in finding better solutions. Some of them were more important, some of them were less important, and some of them we just discarded. Okay, everything was written in C++, and we tried it on two sets of instances. For the smaller one, we actually did the exact solver, and then we tried comparing it to this VNS algorithm. And VNS was much much better to say. Um, in many cases, it found the same solution that was proven optimal by this exact solver, but in much shorter amount of time. And sometimes it actually found better solution. Um, this maybe sounds strange. How we find the better solution from the optimal one? I didn't say that Cplex was this exact solver was also limited in time. I think it was several hours. So at some point, even if it didn't give us the optimal solution, even if it did not prove the optimality of the solution, we decided to accept the best found so far. So not all of them were solved to optimality because, as I said, it takes a lot of time. So in some cases, VNS was able to find better solutions. The problem would be if the solver found the best possible solution and then VNS found even better. That would mean that we made a mistake in our metaheuristic. On larger instances, we didn't actually even try to use the exact solver because it's just it cannot even give us the first feasible solution. It's just too much for it. So we compared ourselves to something to a method that we found in the literature that was state of the art metaheuristic for that problem. And it was this adaptive large neighborhood search. And okay, of course, we found some better results. That's not the point here. Uh, the the main thing here is that it's very easy to just switch from one heuristic to the other. You just change the object. So that's the main thing about this talk. Um, it is the fact that you can actually use different ways to solve these optimization problems from these exact ones for which we did say that they are highly um, impractical for larger instances, or we can actually implement these much quicker procedures, much quicker algorithms for finding good enough solutions, and they actually work great. And you would basically it's a standard to use C or C++ for these methods. So while I wouldn't actually go into the code itself, it is basically standard for them to be implemented this way. Um, of course, sometimes we use prototyping in Python to decide whether some idea for these metaheuristics have any merits, or to just discard it completely, because of course it's much quicker to write something in Python. But when you decide that something is probably a good idea, you would want to implement that in C or C++, whatever you prefer. I generally use C++ for this type of problems. So that would be basically it. Thank you very much. Do you have any questions?
Okay, one question for me. So I assume you only talked about single objective optimization. Did you work on problems that require multi-objective optimization? Does there any of these solvers support that?
Thank you for the question. Actually, all of this can be used for multi-objective optimization. I mean, metaheuristics. When it comes to this exact solvers, you would probably combine those objectives into one, and then you would probably optimize them together. There are ways to do multi-objective optimization. You need solvers that support that. When it comes to metaheuristics, yes, and in fact, the version of this problem that ended up being my dissertation is multi-objective. Um, if I remember correctly, we tried to minimize the distances traveled, penalties from missing time windows, and the third one was yeah, because we actually had fleet of different vehicles. Some were electric and some were regular vehicles. So the third objective was to actually minimize the use of regular vehicles. So yes, this can absolutely support multi-objective optimization. In this particular instance, it was not implemented because mm, at this point I wasn't researching that, but later we did expand this work into multi-objective optimization.
Questions. Another one from me. Uh, are you familiar the implementational details of these solvers and, for instance, how they did the parallelization of the work and searching for the solution?
These exact solvers. Okay. Um, I mean, when it comes to metaheuristics, sure, I'm familiar with the implementation because I have to write it. But when it comes to exact solvers, uh, I'm familiar with algorithms that are used, but I'm not familiar with the implementation itself. When it comes to parallelization, yes, they all support, absolutely, they support parallelization. And you would have to actually use it. But I think that here I did not use parallelization because I wanted to control the processing power just for the research sake. And since metaheuristics were using just one thread, I set the exact solvers to use one thread as well. But of course, in practice, you would use parallelization. Still wouldn't help much because if you have something that takes 10 days, even on 10 threads, it's gonna last a day at least. But uh, these algorithms can be parallelized. These are mostly branch and bound, branch and cut, cutting planes. Um, they can be parallelized, but it's not that simple. I mean, there is some overhead.
Did you? Sorry, maybe I have missed the bit. Like in the time locked loop where you check that like you loop over specific time bound, right? You mentioned that you want to sort beforehand like possible solutions for the best case, right?
Sorry,
When you loop over solutions, when you try to find it, in the time bound loop, when you check that you don't exceed this time.
Oh, for local search.
Yeah.
Oh.
And you mentioned that you want to start from like better solution first. Like you have some like metric to figure out which solution is more promising, right? How do you sort them based on what?
You see, when you're trying to optimize some problem, you're optimizing it based on some criteria, which is the fitness function or objective function, which is defined when you have a solution. It actually maps it to some numerical value, and the solution which has, for example, lower value uh, in terms of minimization is better. So yes, you're always starting. You want to start from a better solution because then you're halfway there. Not maybe halfway, Ali, but you're closer to the optimal one. So the closer you are, the better it is. Not necessarily though, because maybe um, it is a local optima. Maybe it's best in that area, and you go further and further exploring that area, but the overall best solution is somewhere out there. So it could happen, and we have this mechanisms of escaping local optima. For example, that shaking step that just wants to find some random solution that is distant from the current one. It is designed exactly to escape this local optima. But as per your question, yes, we can actually sort it from best to worst based on their fitness function.
For those meta heuristics that you presented, did you try any of them in trip design,
Uh,
specifically in layout or placement phases?
mm,
So when trips are designed,
yeah.
you need to find like there's a similar problem of finding the best placement and best graph.
Oh, okay, okay. Well, no, I haven't worked with that problem, but yes, yes, that would be very interesting. For example, mm, uh, I think that I think that can be also used like from those maxilla chips. Actually, that is a little bit different, but yes, that would be an optimization problem. It would be very interesting to see, but I haven't researched it so far myself. But thank you for the idea. I might actually, do such research. Sometimes the hard part is finding the good benchmark instances. So I have to start with that. For this problem, I would have to see whether actually there is some good benchmark. If not, whether we can actually create some. That would be even better. If you propose some benchmark set of instances, that would be great. But no, I haven't actually done that research yet.
Any other questions? Thank you, everybody.
Thank you all for coming.